Hello again, friends. Here's video number 2. I'm going to go through example 2 and example 3 in this video here. Okay, so example 2, it says in a circle, we have chords A, B, and C, D intersect at point E, and then it gives you some lengths, and I want to find the length from point C to E. So, but we don't have is a picture, which is not a problem. I can make one. So let me grab my shape tool and let me get a circle that I can put in here. So I'll get something like that, okay? So here's my circle, and then I'm going to add to this nice pink circle a couple of lines that are segments that represent chords. So remember, the definition of a chord means the end points of this segment have to each be on the circle. So I'm going to go from one point on the circle to another. Now, it doesn't tell me where this chord is, so I'm just going to take a guess. I'll call this one the one from A to B, and then I'll draw another one that intersects. See, the chords have to intersect, so I'm going to draw another chord that's intersecting with this one. That one's going to be called the chord CD. So let me do that here. So here I said this one's going to be the one from A to B, and then I have the chord from C to D, and they intersect at point E. Now, just so you can tell, the point E is just some point inside the circle. And I drew my chords this way to make it so that it doesn't look like E is the center. E is not the center. It does not have to be the center. If it was the center, then these lengths would be much easier to find. But what I'm going to use now is it says, hypothetically, let's say the length from A to E was 21. So my picture might not be drawn to scale, but we're going to go with it, what I have anyway. The length from E to B is 5. The length from E to D is 7. And we want to find what the length from C to E right here has to be. I'll call that X. So again, just like we saw in example 1, there's got to be something that helps me compare these lengths, some way that I can compare how big X has to be if AE and EB are 21 and 5. And there is a way, okay? And to do this, we have more options. Remember, in example number 1, I drew extra chords in my diagram to create triangles. And I'm going to do the same strategy here. Example 1, though, I pretty much could only draw, I can only connect 2 more sets of points to create 2 more chords. Now in this one, I could draw 4 more chords. I can connect C to A to D, D to B, or B to C. I have all 4 of those choices. But I'm looking for ones that I can create triangles that would have to have some kind of relationship with each other. And so if you kind of try it and it doesn't work, then we'll have to just try something different. So let me use a different color here to show the segments that I'm going to add to my diagram. I'll use purple. Now, you can either choose one or the other, and it seriously won't make any difference at all, but I am going to connect the point C to the point A. Okay, and then I'm also going to connect. So by doing that, I want to kind of find A to D wouldn't be as helpful. C to B would not be as helpful. But if I go from D to B, it would. And let me show you why this choice is helpful. Is now if I look at the angles that I just created. See, remember how like the points C, A, D, B, all 4 of those points are on the circle, and since they're all on the circle, I just created 4 inscribed angles. And more than that, I have like this inscribed angle that's at point C. That inscribed angle would be exactly half of the arc from A to D, because that's the relationship that inscribed angles have with their intercepted arc. Okay. Likewise, I have another angle. Let me choose, how about blue? I have this angle over here at angle B, and that angle intercepts the arc from A to D as well. So what does that mean about those angles? It means those angles must be congruent to each other, because whatever this arc happens to measure, these angles are each half of that number. So whatever that is, it's half of the same number, therefore they're the same. Okay. Likewise, we have these angles that are over here. You have the angle A intercepts the arc from C to B. And you also have the angle D that intercepts the arc from C to B. Now I'm only putting like one curve in each of these because I'm kind of color coordinating. So A intercepts the arc C to B, angle D intercepts the same arc C to B, so that this angle A has to be congruent to that angle D. Let me write a little note as to why this must be true. So just as a note, the angle A has to be equal to the angle D because they are both inscribed angles that intercept the same arc. Angle C is equal to angle B for the same reason. They are both inscribed angles that intercept the same arc. Therefore, triangle ACE, that triangle right here, must be similar to triangle DBE by the angle-angle similarity reason. And now, since those triangles are similar, I can do this. Since those triangles are similar, those corresponding sides must be in proportion. And that is my equation that I can use to help compare these lengths and help me figure out what that length from C to E must be. But again, I need to get rid of one of these ratios because one of them, I can't have two equal signs in an equation. I can only use, I only have to compare two of the three ratios. So the one I want to get rid of is the one that I don't have any information about. Again, it's the ones that I added, these lines that I added to my diagram, the one from A to C and D to B. I'll get rid of that. And then I just substitute what I know. The length from C to E is the one I'm looking for, X, over the length BE, which is 5, is equal to the length AE 21 over the length DE, which is 7. Okay, so now I can solve this equation. Again, use your equation solver, cross multiply, do something, solve that equation. So X is the length of CE, which is 15, and there's my answer. Okay, so here's me, I had to draw the picture, I had to find my triangles, the whole works there, okay? How about example 3? In this one, we have a diagram of circle A, and secants, CDB and CFE are drawn. I know that the length from C to B, so that's the whole length of the secant, let me put that like this, is 12.1. And the length from C to D is only 5.6. The length from C to E, that's this whole secant here, is 11.6. How long? Find the length of the segment from C to F. I'll call that X. So this one I think is probably the most difficult of the three that we've done so far. And because this one, again, I'm going to compare these lengths by finding some triangles that have to be similar to each other. So the strategy is going to be the same, but the execution is a little different. Because in this case, it's not as obvious which chords I need to draw in order to create my triangles that are similar. I have more choices, and then it makes things more difficult. So, I could connect the points from D to F and to B to E, and I would end up having two different triangles there. But as it turns out, I can only prove one pair of angles that are congruent in those two triangles. Instead, I am going to crisscross my lines here, and I'm going to connect the points D to E to make this chord, and then the points F to B to make that chord. And so now you can see I do have two different triangles in this picture. I've got a triangle CBF. Okay, this point right there is not named, so I'm not going to focus on that point at all, but CBF is a triangle, and then CED is a triangle. So let me trace those two, and so we can kind of see them a little bit better. So we have from C or B to C to F is 1. And then how about green? From D to E to C is my other. Okay, so now with them traced, you can see at least I have definitely one pair of angles that has to be congruent. That's the angle C. They both share angle C, therefore that angle is my reflexive angle, and it has to be congruent in both the purple and the green triangles. But what other angle must be the same? Now, we know nothing about when a secant meets a chord. That angle that's at point F, the angle CFB, we cannot do anything with that angle because we don't have any way to compare that. On the other hand, the other angle in this purple triangle is the one at angle B. And that angle is an inscribed angle because point B is on the circle and it's formed by the chords DB and FB. So this angle that's right here has to be exactly half of the arc DF. And this arc DF is also the arc that is intercepted by the angle E that's in the green triangle. So since both the angle B is inscribed and intercepts arc DF and angle E is inscribed and intercepts arc DF, then the angle B must be congruent to the angle E. And now I have two pairs of angles in each of my triangles that must be congruent to each other. Okay, let me write a little note about that. So angle C was congruent to itself by the reflexive property. Angle B was congruent to angle E because both are inscribed angles that intercept the same arc. So the triangle CBF must be similar to triangle CED. And since the triangles are similar, now we can do this. The corresponding sides must be in proportion. And just like I've done before, I want to figure out which of these ratios am I not using in this case. And I'm going to not use the ones from B to F and D to E. Those are the ones I don't have any kind of lengths for. So BF and DE is this one right here. Let's get rid of that. And then just substitute what we do know. Do we know the length from C to B? Yes, it's 12.1. Do I know the length from C to E? Yes, it's 11.6. How about CF? Yes, it's X. And CD is the 5.6. Okay, so again, there's my equation. Cross multiply, solve with your equation solver, see what you get. So cross multiplying, I ended up with this value for X, but again, since my given values were to the nearest tenth, I rounded my length of CF to the nearest tenth. I called it 5.8. All right, so there's when I have two secants, and that's the video number 2 out of our 3-part video series.